All right, we're starting here with the second part of section 2.3. We're going to look at derivatives of trig functions, and we're also going to look at higher order derivatives, which is just taking a derivative for the second time or a third time. So we'll look at that a little bit. First of all, we have the derivative of trig functions. Is what this chart said, or what our notes say is the derivative of tangent x is secant squared x. Derivative of cotangent is negative cosecant squared x. Derivative of secant x is secant x tangent x, and the derivative of cosecant x is negative cosecant cotangent x. All right, and we still have the same rules, the product rule and the quotient rule. So we'll go ahead and we're going to find the derivative of a here. We know from our rules of derivatives we can take the derivative of this first one and take it to the derivative of the second one, and we can do them separately. So the derivative of x is just 1, and the derivative of tangent is secant squared x. So a is done already. That was pretty quick. B down here, well, this is saying x times secant x, so that means we have to do the product rule. The product rule says we can take the derivative of the first one, which would be 1, take it times the second one, add, then the first one times the derivative of the second one, so the derivative of secant x is, up here, is secant x tangent x. We probably could simplify this to be, so I'd have secant x plus x times secant x tangent x. I could probably pull a secant x out and have 1 plus x tangent x. So I suppose we could do that. It doesn't matter. The last one here, 1 minus the cosine of x over sine x. If we remember way back to our 8th grade math days or before, in order to add or subtract fractions, we gotta have to have a common denominator. So really, we could rewrite this as 1 over sine of x. The common denominator, they're both under, sine x is both under both of these. This is the denominator for both of these. Minus cosine of x over sine of x. If we remember our trig from last year, 1 over sine of x is the same thing as cosecant x. And cosine x over sine x is the same thing as cotangent x. Now we can take the derivative of this. We can take them separately. From our notes above, we know the derivative of cosecant x is negative cosecant x cotangent. All right. And we know from up in our notes above that the derivative of cotangent, so this would be minus the derivative of cotangent, which is negative cosecant squared x. So in order to simplify, I guess, again, we could have cosecant squared x minus cosecant x cotangent x. And there's that derivative there for C. All right, higher order derivatives, and where this comes into play is we know if we're given a position function, we know if we take the derivative, we automatically get that object or whatever, we get its instantaneous velocity. So we get its velocity when we take the derivative of a position function, we get its velocity. We take one derivative, we get its velocity. We take that derivative again, and we get its acceleration. So we can know that the exact acceleration of that object at some point in time. All right, and all we have to do is just take a derivative and then take our derivative again. Remember we did this last year in pre-calculus when we were trying to find the point of inflection, and that'll actually come up in chapter 3 in this book when we're talking about concavity and all that stuff. But anyway, just as a refresher, we want to find the second derivative of this equation right here. So first I got to do the first derivative. So I'm going to have, let's see, 9x squared minus 10x plus 2. And then to find just the second derivative is simple. I'm just going to take the derivative again. I get 18x minus 10. And that answers our question. Okay. So we have one last example here. the velocity of an object in meters per second is via t equals 36 minus t squared. Notice now they gave us a velocity. We said the derivative of the velocity is the acceleration. And really what they've done for you, they've taken the derivative of the position function and got our velocity function to be 36 minus t squared. So what they want us to do, they want us to find the velocity and acceleration of the object when t equals 3. Well, they've already given us the velocity function, so we can go ahead and answer the first. Find the velocity when t equals 3. We can do that right away. We just go ahead and we plug 3 in here. So I have 36 minus 3 squared, which is 9. So our velocity of our object is going to be 27 meters per second. All right. Well, to find the acceleration, then we just take the derivative of the velocity function, which is actually the second derivative of the position function. But anyway, we take the derivative of the velocity function, so acceleration is going to be the derivative of the velocity function. So it's going to be, well, derivative of 36 is 0, negative 2t. So to figure out the acceleration at this time right here, the acceleration, we plug t in, so our acceleration is going to be negative 6. All right, so that answers that question there. Hopefully this all makes sense to you. And here's our assignment that we post on the website as well. And we'll see you next time.